Good. The key word there is it keeps repeating. Okay, if you look at the width of the repeating section, okay, it looks like it keeps going. If you want to, can you please go into your window and just change your minimum to, for example, negative 720 to 720. Okay, so negative 720 to 720. Don't change anything else. Once you've done that, graph it again. You get that situation. Okay? Can you see that? Just all we've done is that. So it's got on the screen, but it's exactly the same. And we can keep doing that. We can keep going wider and wider and wider and wider. And what's going to happen is that graph will not look any different. Okay? That's what we call a periodic function. It just doesn't change the look of it. If we graph any other type of function, if we graph, for example, if we graph y equals x squared, right? If we graph y equals x squared, we all know that the graph of y equals x squared looks like that, right? And if we go wider and wider and wider, the graph just keeps getting taller and taller and taller. It doesn't repeat. Right? This graph repeats itself, whereas this graph doesn't. Once you've reached that stationary point, you never get another one. Okay, whereas there's a turning point there, there's one there, oh, there's another one, oh, there's another one. Okay, it's like a goldfish. Oh, there's a diver. Oh, there's a diver. Right? It's an old joke. You'll look it up, ask parents. So, okay, what we've got there is a graph that keeps repeating and repeating and repeating. Now, a sine function is an example of a periodic function. Okay, if you just go back to the y equals menu again, change sine to cosine. So just put cos x and graph that and see what it looks like. What do you get? It's kind of the same, isn't it? Kind of, but there's little differences. Okay, in terms of the height, it's exactly the same. Okay, in terms of how often it repeats itself, is it the same? Okay, is it the same? Like I got the same number of hills and troughs as I did with the sine curve in that window. Go back and redraw the sine if you're not sure. Okay? So if you look at the coast, it starts there. So how long does it take me to get back to the same place? 3, 4. So I've got 4 full waves there. Can you see that? If I do the sine curve, it just starts in a different place, but I've got 4 full versions of the wave. So it's exactly the same length too. It just has moved across a little bit. Right? So what do we call it when we move a graph to the left or to the right? A translation. And specifically, horizontal translation. Good. Okay? So it's a horizontal translation. So the sine curve and the cosine curve are exactly the same. They're just moved. Okay? 10. Have a crack at that one. So if you haven't done, obviously I'm guessing Brendo has. So go back to your y equals, change cos to tan, and graph that little baby. Okay, now let's make it a bit easier for ourselves. Change our window back to minus 360 to 360, just so we can just narrow it. Please. Okay, this is just a remnant of another graph. Ignore that little blue line there. I've got to clear that later. I don't know what it's there for. Okay, can we see what's going on here? Right? Now, what this graph doesn't show us is what's going on here. Okay? So we can explore that a little bit. Let's change our window. This time scroll down to the y minimum. Right? And put minus 100 to 100. Minus 100 to 100. But change your scale to like 10, just otherwise it looks really disgraceful. Okay? And do that, and then graph it. Okay, the calculator gets a bit excited and can't do any more. Okay, can you see what's going on? So what x value is this value right here? Can you see where I'm pointing? What x value is that value there? Think about your full scale. What is that point? So what's this point over here? What's the x value over here? Right on the end of our screen, right-hand end of the screen as you look at it. 360 degrees. Remember, we're in degrees. Because trig functions work with degrees, right? If you want to find the sine of a number, that number has to be an angle. Correct? Yep. Because we learnt that in grade 8. So, that's 360. So what's this value over here where that first funny looking bit happens? Work it out. You know what the scale is. You write the scale in. What was your scale? 45. Right? See, the scale is 45. What that means is each of these little lines, little hashes across the x-axis are 45 degrees long. So, for the third time, what's that value there? 90. What's the tan of 90? What's the tan of 90? Good afternoon. What's the tan of 90? Anyone? Do it. You've got a calculator in your hand. Okay. We're getting errors undefined here. That's a bit nasty. Come on, let's do this. Let's talk about the tan of 90 here. Right, let's talk about what's going on. 90 equals some weird looking, don't know. What does your calculator actually say? Undefined. Yeah, undefined it says, if you do that on your calculator. Tan of 90, why is that backwards? Oh, the screen's backwards. It's just weird. It's actually flipped. I have to talk to Scotty about that. Okay, the tan of 90 is undefined. Why? What does that mean? Has anyone ever thought of this before? Have you ever thought, I'm doing trig and I get tan of 90 and it gives me a number and you don't go, oh, okay. Have anyone ever actually thought about it? What's tan equal to? What's the ratio for tan? Thank you. The tan ratio, do you agree, is opposite over adjacent. So here's my little right triangle. There's my angle theta. Right? So this is my opposite side and this is my adjacent side. Yes? Right? And we know that the tan of theta, the angle, is the ratio, the length of the opposite side divided by the length of the adjacent side. Is that okay with everyone? So if I find the tan of, so for example, if I find the tan of 45, so this is a 45 degree angle, what's the answer? On your calculator, what's the tan of 45? Em, what are you doing? Are you like doing this or are you doing something else? Because if you're doing something else, you might as well go to the library. And you're welcome to. Good luck with that. Okay, so what's the tan of 45? 1. So what does that tell you? If the tan of 45 is 1, what does that tell you about this triangle? Nothing? Go. Guess.
The two sides are like the same.
Exactly right. If the tan of 45 is equal to 1, so what we're saying is tan 45 is equal to opposite over adjacent, right? That's equal to 1. Right? Tan of 45 is equal to 1. Do we agree with that statement? Yes? Your calculator's given you 1? Right. That must mean that the opposite side and the adjacent side have to be the same length. Because any number divided by itself is 1. Right? So there's a little bit of... Have you ever thought of that? No? Good. Damn it. All right. I was hoping someone would have thought of it sometime ever. No, apparently not. Okay, so what we're saying there is when these are the same size, then we get 45 degrees there. Okay, so as the theta gets bigger and bigger and bigger, what's happening to the opposite side? Okay, let's keep the adjacent side the same length. So I'll scroll down a bit. So let's keep my adjacent side, right? So if I make a triangle like that, right? There's the theta there, right? So there's the little triangle here, right? There's my opposite, there's my adjacent. I'm going to keep my adjacent side the same length, and I'm just going to keep doing this. What's going on with the opposite side? It's getting bigger. Do we agree with that? As I make my theta bigger, this side is longer. We all okay with that? Yeah? So as I keep going up and up and up, right? So there's a big angle, right? My adjacent side is getting, my opposite side is getting longer and longer and longer and longer. Do we agree with that? Yes? So big number over small number means my ratio is going to get bigger. Like do the tan of 60. What are you getting? So is it bigger than 1? Yes, no, do the 10 of 70. Is it bigger again? Yes, it is. As you keep going, so do the 10 of 80. Getting bigger again. Do the 10 of 85. Are we getting bigger? Are we getting bigger? Right, do the 10 of 89. Yeah, pretty big number. Do the 10 of 89.5. And stop there for a moment. Now you're getting quite a big number, aren't you, not? So what's the 10 of 85? Just for a few. 10 of 85 is what? 11.4. Okay, so that's quite big. And if we keep going bigger and bigger and bigger, that number's going to get bigger. Let's imagine what that triangle looks like. Okay, now, in order to do a ratio, we need to have a right angle. Do we agree with that? Okay, so this is my opposite side, this is my adjacent side. Okay? If I want my angle to be 85, right, that's pretty close to perpendicular. Do you agree with that? Yeah? So what happens when that angle, this angle here, what happens when that angle becomes 90 degrees? It's not a triangle anymore. Yeah, exactly. How many degrees in a triangle? 180. So I've already got the 180 all taken care of. I've got no more angle. So I don't have a third angle. 89.9, okay, it's going to be really tall, but there is a 0.1 of a degree at the top. So it's still an angle, so I can theoretically make that triangle. It's going to be really tall, but I could do it. Right? So what's going on is, by the time you get to tan of 90, you don't have any angle any left. So you don't have a triangle. Therefore, the tan of 90 doesn't exist. You can't do it. Think of it this way. We also know all about gradients, correct? The gradient of a line is change in y over change in x. Rise over run. Look at the way I'm doing my arm. Rise is opposite. Run is adjustment. Okay? If I have a vertical line, what's the gradient? You can't have one. It's infinity. Right? Because it's so steep, I don't have a gradient anymore. It doesn't exist. So the tan of an angle and the gradient are related because of the same formula. Rise over run. Okay? So the tan of 90 doesn't exist. So if we go back to our graph, that's what's going on here. Right? It just doesn't have a value. Do the tan of 91. So just past 90. What do you get? Negative what? Negative 57. Do the tan of 89. What do you get? 57. Ooh, isn't that interesting? Is it exactly the same lot of decimals? Except one's positive, one's negative? Oh, isn't that interesting? So, apart from the negative sign, there appears to be another value that has the same ratio. Tan 89, tan 91. Just for argument's sake, do the tan of 269. Tan of 269. What do you get? You get the same number, but it's positive, isn't it? So there's a tan of 89, gives you 57 point blah blah blah, and you've got the tan of 269, some sort of random number that I just pulled out of the air here. Not, right? But I've just grabbed this random number and said, try tan of 269, and you get, the same number. Amazing. All right? What we're going to look at in this unit is, why? Okay? But what the reason is, quite simply, is because those three trig functions, sine, cos and tan, are periodic. They repeat themselves. Okay? So let's reset our calculator back to how we started. So put your y values back to -2 and 2, and we're going to go back to the easy functions. And your scale is 0.5 again, just so we've got numbers. All right? And then we're going to we'll go back to graphing sine. Okay? So you put it all back together so it looks, again, like that. And we're going to talk about what we've just seen there. Okay? So we've got a situation where we've got a sine function that repeats. Okay? Where's 90 degrees? In this function, where's 90 degrees? Like, if you had to point out, where's 90 degrees? Where's 90 degrees? X value is 90 degrees. Where is it? Tell me how to get there. Is it over here? No, is it up there? So tell me how to get there. Go.
Like in the middle of the first wave.
What do we call this point here?
Origin.
Right, can we use the origin as our point of reference? So where is it from the origin? 2 dots that way, yes? Remember we got 45 degrees, so that's 90. So there's 90 there. Okay? So what's the sign of 90 on your calculators? 1. What's this value here on your calculator? 1. Remember you've got a scale of up to 2 and going up in 0.5, so this is 1 there. Do we agree with that? So if I go the sine of 90, I get 1. So that's what the graph is telling me. Okay? What's the sine of 180? 0. That's that point there. Right? 45, 90, 120, 135, 180. Right? 0. What's the sine of 270? Negative 1. Alright? So point there. What's the sine of 360? 0. Back to the start. Now, what's the thing that's the same about 0 and 60 degrees? They're the same, aren't they? Because how many degrees are there in a circle? 360. So if I start at 0 and I rotate 360 degrees, right back where I started. Okay? And that's what this graph is showing you. If I go 360 degrees, I'm right back where I started. If I go 360 degrees the other way, right, negative, back where I started. Boom, back where I started. Okay? So these things repeat and repeat and repeat. Do you get what I'm getting at here? Yeah? Okay. So that's how we read the graph. Okay? This is our angle, and this is the ratio. Because when you go sine of an angle, you get the ratio. Opposite over adjacent, adjacent over hypotenuse, whatever. Right? For the 3 different ratios. This is sine, so this is opposite over hypotenuse. So this is the ratio of the opposite side to the hypotenuse. Okay? And there's those values on that axis there. And as you can see, so how many times can the ratio in that from 0 to 360, how many times does it equal 45? Max is saying twice. Okay, so here's 45 there. So if I find the sine of 45, I'll get that value, whatever it is there. Are we okay with that? Does that value for y ever occur again in a circle? So the circle's from there to there, remember? Does that point ever occur again for the y value? So if I put a ruler here, does the graph ever cross the ruler again? Yeah, there. Doesn't it? So there are 2 values that give you the same ratio. And you discovered that a minute ago when you did with tan. Right? We're going to get to all this. This is all what we're coming to. Right? Because trig keeps repeating itself. And in fact, how many of these values are there on the whole sine function? How many times will I come across that height on the sine function if I kept going? Sorry, leader? Go on, say it. Infinity. 100%. Right? Just be a little bit louder. All right? You're right. Because I just keep repeating and repeating and repeating and repeating and repeating and repeating and repeating. So if I don't limit my domain, I'll get that value an infinite number of times. Okay, so what does that tell us altogether? So let's look at some terminology so we know what we're talking about here. Okay, so here's an example of a periodic function. Okay, don't worry about the function notation, I just want you to look at the graph because there's some terminology that you need to become familiar with. Now those of you who do physics, you'll be doing waves, correct? So some of these terms you are already familiar with. You should already be familiar with the term period. You should already be familiar with the term frequency. You should already be familiar with the term amplitude. Okay? Those of you, which is the majority in the room, don't do physics, we're going to learn what they are all about now. Okay? Those doing physics are studying things like sound waves, light waves, water waves. Okay? If you hear the word wave, that is defined by a periodic function. All of you, I'm sure, in the last 24 hours have listened to some form of radio. Had the radio on in the car or at home or whatever, yes? Radio waves. Okay? Now, as an example, who listens to, I don't listen to them, but who listens to Nova, for example? Okay, do you know what the frequency is of Nova when you turn on your radio? Yeah, the number, yeah. 106.9, thank you. Okay, so I couldn't quite remember, that's why I asked. Okay, 106.9. Anyone know what that number actually means? Apart from it's where it is on the dial? Anyone? No? No one. Excellent. Okay. So, what you might do, if you've got an old style radio, you might actually see that in the corner it's got the units of that number, and the units are capital MHZ. Okay, physicists, what's the HZ? Hertz. Okay, named after a German physicist named Frank Hertz, Hertz. Okay, Hertz. What's the big M? Mega. What's mega mean? No. Million. Goodness me. Okay, yes, it is big. Right? Morons. Right? Mega means million. So 106.9 megahertz means 106.9 million hertz. What's a hertz? What does hertz measure? Frequency. Okay? Hertz measures frequency. Okay? Now let's think about what frequency... So what does the word in general... Physics students, just be quiet for a moment. Those of you who don't do physics, what does the word frequency mean? If you hear something happens frequently, what is it doing? Yeah, so how often it occurs. So the frequency of something occurring is how often you get it to occur, right? In physics, it means... So the frequency is how often does it repeat? And what the actual definition is cycles per second. It simply means how many repeat itself. Right, so one cycle is if I start at a crest, that's a trough. Okay, we all okay with that terminology? Right, crest, pretty obvious, it's a mountain, trough, valley. Okay, so how often do I do that? How many times do I do that in 1 second? So if you think about that number for a moment, if you tune your radio to that frequency and listen to Nova, right, then the signal that's coming in from the repeater is repeating itself 106.9 million times a second. Right? Now, that's on the FM band. You all okay with the FM versus AM band? Yeah? So FM is most... Yeah, good. Okay, so... do you understand the idea that if you listen to something on FM, the signal is a lot clearer than it is on AM? How many of you have grandparents that listen to AM? 4BC, 612A... Oh, my goodness. Okay, do you know there is an AM band? Oh, good. Okay. So there's an old style AM band, which is like what your grandparents would listen to, and some of your parents will listen to the ABC. And you get in the car and go, what the heck is this? And change the channel, right? That's what we call the AM band, okay? So this is important in terms of all this. So this is the FM band, which is where you guys will mostly listen to radio. Triple J, Triple M, Nova, Big, whatever. All those guys, okay? Right? All those guys. And they're measured in megahertz. What that's saying is... And they're clearer. If you ever change to an AM band, the volume goes right down. Have you noticed that? Yeah? And then you have to turn it up, and then when you turn back to FM, it blasts you out of the car because it's too loud. Because the signal for FM is much, much clearer because you're receiving 106.9 million cycles every second. Right? So you're getting a lot of information. But the problem with FM is it doesn't go very far away from the repeater station. So if you're listening to FM and you're heading to the Sunshine Coast, very quickly you lose signal. And you have to go and try and tune into the Sunshine Coast radio stations. Right? But if you're listening to AM, okay, that's called... So this is AM. Like, for example, ABC down here is 612. All right? So it's 612 kilohertz. Right? So it's 612 kilohertz. Kilo means 1,000. So it's only 612,000 cycles per second. So there's a lot less signal. But what the difference is, does anyone know what the A stands for in AM? Pardon? Amplitude. Well done. It's amplitude. AM stands for amplitude modulation. So the AM bands change the amplitude. They change the this way graph. Right? And there's this way that contains all the energy. Right? So if you create a wave, if you think about you go into the ocean, right? And let's say you have a wave coming in every second. So pretty constant waves coming in every second. If the wave's this big every second, you can stand there and take it, most of you. Boom, 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 boom. But if the wave's this big every second, it'll knock you over, correct? Right? Same frequency, still coming in every second, but there's more energy. Right? So amplitude is all about the energy of the wave, whereas frequency is just how often it happens. Right? So AM changes the amplitude. So it changes the graph this way. So there's a lot more energy. You don't get as much signal, so the signal isn't as good, but it goes for longer because there's more energy. So by the time it gets from the repeater station in Brisbane, in the centre, you can listen to 612 ABC right up the coast all the way up to nearly Gympie before it loses energy. Right? Without having to change the channel. Okay? So amplitude, lots more energy, because that's what amplitude is all about, just less frequency, so the signal isn't quite as strong in terms of its quality. So AM, it's a bit more, but you can still hear it. Right? Frequency modulation, FM, it changes the frequency. So the same energy level just changes the frequency, changes how often you get that signal. So you're just changing your receiver to pick up a different frequency. And that's all you do. Old style radios, you see that little line that used to go across the bar. You know, you go to your grandparents' place and you change the dial, and that little line used to wind across. Have you ever seen those radios? That's all you're doing. You're just changing the resistor, and it's just picking up a different radio station, picking up a different frequency. Right? That's all it's doing. Okay, there's a little circuit inside it that changes how you pick up that signal. Okay? And that's all you're doing here. Right? Change from AM to FM, you're just changing the circuit to pick up a different set of signals. Okay, so frequency, how often a second? So how many cycles a second? Amplitude, energy, this way. Okay? Does that make sense? Yeah? So where do we measure amplitude from? We measure amplitude from what we call the mean position. Okay? Now, if you remember when we looked at all of our transformations earlier in the year, we talked about what's the key point that we're going to move in order to look at this translation. So if we're looking at the x squared, it was our stationary point. Where does the stationary point go? Okay, does it go up? Does it go down? Does it go left? Does it go right? Do we flip, etc., etc., right? So that was our key point. When it comes to periodic functions, sine, cos and tan and all of its variations, the key the middle is the mean position. So it's where it starts. So in this particular graph, as you can see, the mean position's at 1. Right? Because we've got exactly the same distance up from 1 up to 4, so 3 units, right, as it goes down from 1 to minus 2, which is 3 units. So its mean position is at 1. So the amplitude is measured from the mean position to the peak and the mean position to the trough. Okay, does that make sense? So that's how you measure amplitude. All right? Frequency we've already talked about. Frequency is how many times per second does this occur? There's a related measure which we call period. Okay? What is a period? So what, just in general, in English, what does the word period mean? That's not a good look from here. All I can see was my belly. That was shocking. Sorry, Tyler. All right? What does period mean? What's a period? We're in period 1. What does that mean? Michael? Yes, thank you. That's what I'm trying to get to. So what does it mean? What's a period? It's a set given length of something, isn't it? Right? So a period is how long, in a periodic function, how long is one cycle? So how long does it take to go from there back to there again? So if we look back at our function that we were looking at earlier, the sine curve, what's the period of that graph? How long does it take for that graph to repeat? 360 degrees. Yes? So that graph repeats itself every 360 degrees. So its period is 360 degrees. How long does it take to repeat? Now how long does not have to be time. It generally is, but it doesn't have to be. It can be a period, in this case, it's the number of degrees. Okay? What's this graph's amplitude? 1. Okay, you all set up your graph, you know that they go up in halves, so that's 1, that's 2, that's minus 1, that's minus 2. The amplitude is 1. Where's the mean position? Yeah, be more specific. 0 can be, that's not the mean position. That's a point. Where's the mean position? It's the whole axis, isn't it? So what do we call that line? The x-axis. Do we not? So the mean position is the x-axis. Now for a periodic function, because it keeps going and going and going, it can't be just a point. It has to be, in this case, a line. And that whole graph moves up or down along that line. So the mean position is the x-axis on that curve. Okay, so if we know that the period is 360 degrees, we know the amplitude is equal to 1 unit. Okay, the one thing we haven't talked about, what's the frequency? So what's the frequency of that curve? So how many cycles per second? So how can we work it out? Any ideas? Do you know the answer? Go. Good. Excellent. That's all I wanted. Yeah. So frequency is defined to be, now, period has the symbol capital T. Don't ask stupid questions. All right? Period has the symbol capital T. Amplitude has the symbol capital A. Frequency has the symbol lowercase f. Okay? And the definition of frequency is 1 divided by the period. Okay? Because they're related to each other. Because period is measured in seconds, right, generally. Okay, because how long? And frequency is cycles per second. So in our example, instead of being cycles per second, it'll be cycles per degree. Okay? So what we're going to look at is how they're all related to each other. So we're going to come back to that in a moment. Okay. There's some definitions. So let's have a look at this example. On that graph there, what I'd like you to do is I'd like you to write down the following. I want you to write down what's the frequency, okay, what's the period, where's the mean position, okay, and what's the amplitude. Okay, so I'm looking for mean position, that's the first thing we try and find. And then we can do the other three from there. Okay? So frequency, period, mean position, amplitude. What are they? Is the graph big enough for you to see up the back, guys? I can just... A bit better? I'm going to stand here. Whoa! Give units. So in both cases, both axes are given in units, so use the units that are provided. It does. It doesn't hit 50 because it hasn't started. It started earlier. So where's the highest point on this graph? Good. Where's this graph? 10. So what's halfway between 10 and 50? I'm just ignoring you now. What's halfway between 10 and 50? 30. How do you find halfway between two numbers? Add them up, divide by 2. Okay? Alright. We'll continue this on Monday. That's where we've got to. Can you please make sure that you're focused this weekend? We'll finish this question on Monday too. focus this weekend is getting that draft finished for me. All right? Have a good afternoon, guys.